What's up, guys? This is Chris McCormick. In today's video, we're going to be looking at how you apply BERT to the task of question answering. And specifically, we're going to look at the Stanford Question Answering Dataset. And if you're familiar with that benchmark, we're going to be looking just at version 1 of it in this video. Maybe version 2 we'll save for another one. So I'm going to be going through the details of like how you apply BERT to that benchmark. And then I've also got an example notebook that I'm going to take us through where we're going to take a model that's already been fine-tuned for question answering, and we can give it our own text and our own questions and see how well it does. So when I was first learning about BERT and trying to make sense of it, a lot of the hype around it was kind of bewildering, and I think question answering is probably the best example of that. So you could see a headline like this: new AI model exceeds human performance at question answering. And if you're not familiar with the SQuAD benchmark, I think it's easy to read that as like, okay, so I can ask BERT a question and it's going to give me an answer back that's indistinguishable from a human answer, right? That would be like the first true AI, I believe, and we're not there yet. So the actual task that's implied here by question answering is much more constrained. But it is still really impressive what BERT is able to do on this task, and I think it's interesting to see kind of the details of how you apply it. All right, so first off, let's look at the SQuAD benchmark. So the acronym stands for Stanford Question Answering Dataset, and the U comes from question. And the homepage for this dataset is really great. It's got this nice explore feature that lets you see examples from the dataset and then example model predictions too. So that's what we're looking at here. The SQuAD dataset consists of passages of text taken out of Wikipedia articles, like this one on Super Bowl 50. And then they've got this big collection of questions written by crowdsourced workers, where the answer to the question can be found somewhere in the reference text. So every training and test sample in the dataset consists of a reference passage and a question. So if I wanted to know who won Super Bowl 50, I could ask Alexa that question, and she would do a really good job answering it. She would, have the right answer and express it in a very natural sounding way. But Alexa relies on a knowledge graph, right? Kind of this database of well-known facts. So what's cool about the task in the SQuAD benchmark is that the answer comes from this reference text. So it doesn't have to be a well-known fact. It could be something that's really, only answerable by reading this reference. So that's the cool part. The more, the part that's kind of a letdown is that the way the task is defined is that the model just has to highlight a span of text that contains the right answer. So it doesn't formulate this nice natural response. And, it also can't answer a question where you'd have to like combine pieces from multiple sentences in order to answer it. So let's look at a few of these questions because I think it's pretty interesting to see what the models are capable of. So the way this interface works is we've got, for each question, we've got the ground truth answers, which are passages from the reference text that are acceptable answers to the question. And then we've got the model's prediction. And when you hover your mouse over one of these, it highlights, where in the reference text on the left that answer came from. And then it's also highlighting for you what words in that passage also appear in the question. And that's pretty interesting because it shows you where there's maybe words in the question that don't actually appear anywhere in the reference text. So, for example, with this question, which NFL team represented the AFC at Super Bowl 50? The word represented isn't in the passage anywhere. The passage says that the Denver Broncos were the AFC champion and the Carolina Panthers were the NFC champion. But, nowhere does it say like that they represented their respective leagues. So it's clearly, doing some more complex understanding there. Another one I thought was interesting. It technically got this one wrong, but it seems like it got it really close. So apparently the Super Bowl 50, they had called it the golden anniversary, so there was a lot of gold themed stuff. And the word color doesn't appear anywhere in the reference text. And the question is, what color was used? So BERT apparently has, or whichever model this is, apparently is able to understand that gold is a color. So I'd be really curious to explore maybe in another video how much kind of like maybe you'd call it like world knowledge these models have versus just like language understanding. So, as an example, I bet if you masked out the word Broncos in this passage and asked BERT to fill it in, I think it would get it right. I think it would know that Denver's football team is the Broncos. Nick pointed out to me that these models are, they're based on statistical co-occurrences. So they, in their pre-training, they've seen Denver and Broncos together a lot. So it would make sense that they understand like, all right, Broncos and Denver go together. But yeah, it'd be fun to play around a bit and see like what kind of trivia BERT, has in its weights. So how do we actually apply BERT to one of these question answering examples? Well, it's fairly straightforward. We're going to take an example here that I figured it'd be fun to ask BERT some questions about itself and see if it could answer them. So we're going to see in the example code, we'll give it the question, how many parameters does BERT large have? And the reference text we'll use is some text taken out of that same notebook where I explain that BERT large is really big. It has 24 layers and an embedding size of 1024 for a total of 340 million parameters. So that's the answer we're looking for, 340 million. So what we'll do is we'll take all the tokens from the question and all the tokens from the reference text, and we'll pack them together in the input. So we always start with the CLS token, even though it's not used for this task. And then we put in the tokens for the question, and then put in the SEP token, the special token there to separate the sentences. And then we pack in all of the tokens from the reference text. And then part of how BERT is actually able to distinguish the question from the answer, in addition to this SEP token, we have these things called segment embeddings. And BERT just has two segment embeddings that it's learned, segment A and segment B. And all we do is we add that vector to each of the tokens. And then BERT is able to kind of use that information in the embeddings to know that these are all reference text tokens and these are all question tokens. So to actually do the classification, to actually highlight the answer, 340 million, what we have is basically like a start token classifier. So these are all let's say these are all the tokens from the reference text. I kind of rephrased the answer here to make it fit better. And then for every embedding, we're gonna multiply the final embedding by this this vector that I've labeled start. It's kind of like it's the weights of the start token classifier. So we'll take the dot product between the embedding and the start token classifier weights, and then we'll apply the softmax activation function on the output. So that means we'll take this value and take the exponent of that, and then divide it by the sum of the exponents of all of these values for every word in the paragraph. And what that gives us is a probability distribution. All the values will sum up to 1. And if it's working properly, and it does, we'll see that it'll predict the highest probability for the token 340. That's the most likely start of answer token. And then it does the same thing for the N token. So we have this time we have like a N token predictor and a set of weights for that. And if this is working correctly, and it does, we'll predict M as the end of the answer span. Yeah, just to clarify, I had a note in there in the previous slide, but there's only a single in a softmax classifier, like if you're doing it on MNIST with 10 classes, each class might have a different set of weights for each output. Here we actually use the same weights at every position. So there's only this this single start weight vector. Same with the end. All right, so let's take a look at the example code. All right, so this notebook is called Question Answering with a Fine-Tuned BERT, and I'll put the link to this notebook down in the description. So something a little different with this notebook versus other ones I've recorded recently is that we're not actually going to do any fine-tuning of the BERT model ourselves. We're going to use a model that's already been trained on the SQuAD benchmark. And what's interesting is that, I think you can argue that that it'll still perform pretty well on question answering on other subjects because it's learned basically how to perform this question answering task well. So, and in this notebook, we'll give it some text that obviously did not come from the SQuAD benchmark, but it'll still do a good job of picking out the right answers. So we'll be using the Hugging Face Transformers library again, so I have to start by installing that. And then we're going to take this pre-trained model, and the Hugging Face library defines this special class for doing question answering, BERT for question answering. And the name of the model that we're downloading is BERT large, uncased, whole word masking, fine-tuned on SQuAD. Whole word masking, I think, means just that instead of masking out individual tokens, which could be subwords, it always masks out entire words. So a slightly different training regimen than the original. And it is BERT large, not BERT base. So BERT large is really big. Here's that example text that we're going to use. So BERT large has 24 layers instead of 12, and an embedding size of 1024 instead of 768, and a total of 340 million parameters. All right, so we'll load that. It's got a download. It's 1.34 gigabytes. Nice thing to know here is, if you're using Colab, this isn't using your own network bandwidth. It's the Colab instance talking to Amazon AWS to download the model. So Google's picking up the tab. And then we'll load the tokenizer as well. Something that I thought was kind of interesting was that apparently this model has the same vocabulary as BERT base uncased. In the example code that this is based on in the Transformers library, they actually take the tokenizer from BERT base uncased, and it works just as well. All right. So with the model downloaded, we're ready to ask it a question. Our question is, how many parameters does BERT large have? And our reference text is those two sentences. So we start by tokenizing both the question and the answer text. The encode function knows to treat this as a text pair. So it will tokenize these and then add the special tokens and put it all together into one list of input IDs. And together that's a total of 70 tokens. And then we can kind of print out the tokens just to see what's going on in there. Yeah, so always start with the CLS token. How many parameters does BERT-large have? Question mark. And then the SCP token, and then I added in this line break here just for clarity. BERT-large is really big, ... It has 24 layers. All right, you get the idea. Okay, and then we do need to provide the segment IDs to the model. So the way we're doing that is we're gonna look at those input IDs and we're gonna find the location of the SCP token. And then the number of tokens in segment A is SCP index plus 1, and then the remainder of the input IDs is the length of, or the number of segment B tokens. So with those two numbers, we can construct a list of zeros and ones. So number of zeros equal to the number of tokens from segment A, and then number of ones is equal to the number of tokens from segment B. And there we go, we've got our segment IDs list. It should be the same length as the input IDs. Something kind of interesting is that in this example code, they don't do any padding. And I think that's because padding has more to do with processing batches of inputs to BERT. So if you're giving it a batch of let's say 16 inputs to process all at once, then those sentences, or whatever the input sequence is, they all need to be either padded or truncated to the same length. But here, since we're just giving it one input, there's no padding necessary. So we feed our list of input IDs and the segment IDs into the model and do a forward pass. The transformers library likes to use the term token type IDs to refer to the segment IDs. I prefer segment IDs. I feel like that's more clear. But yeah, and then it returns the start and end scores, because remember, this is the BERT for question answering model. So it's got an output that's specific to that task. So what we can do is just find the index of the word or token with the highest score from the start classifier, and same for the end. And then we can take the tokens between those two indices, join them together with space, and print out the answer. And there it is, 340 million. Got it right. So, and then you can also, handle the subwords and concatenate the two to restore the original token or the original word. And then just a small detail here. If you read in the paper, they do something a little more sophisticated than just looking at the highest start and the highest end. The problem with this approach is that it's possible, theoretically, that the highest end token could be, before the highest start token. So it might, using this approach might define a span that's impossible. So what they actually do is they find the combination of two tokens for which the start score plus the end score is the highest. So a little more complex, but we don't need to do that for kind of playing around with it. Yeah, and then just for fun, we can visualize those scores to see what the model's producing. So this is just some code to plot those. We'll take all the start scores and the end scores. Every token needs to be unique in order to use it as an x-axis label for a bar plot. So we'll add the token number to each token to kind of make them all unique. And then you can do a bar plot. So these are the score values for every word in the input sequence. And I was kind of surprised to see, how dramatic the difference is here, right? Like the score is, is positive and very high for the token 340, and then it's actually negative for every other token. And the reason they're negative and positive is that for the purpose of designing the model and training it, we use the softmax function. But when it comes time to actually, evaluate the model, you don't actually need to perform that softmax step. You can just look at the dot product value. So that's what we have here. We're looking at the dot product values. So you could kind of apply softmax to all of this, and it would create a probability distribution. But this is enough to basically pick the correct answer. All right, so we can do the same for the end. So the end, it's a little less certain about. This corresponds to the token 340. This corresponds to the subword M, and this would be parameters and the exclamation point. So it's less certain, but it still got it correct. It knows that 340M is the right answer. So that's pretty cool. Yeah, and then I've got one other view here where I tried showing them together on the same plot. Yeah, it feels I don't know if I like this any better than the separate approach. So blue is the start score, orange is the end score. So the highest end score is here, and the highest blue score is here. Anyway, a few more examples just for fun. Took that process above for tokenizing and setting the segment IDs, and then generating the answer, put it all together in one function, and then we can play with it a bit and try out some different stuff. So what I'm using as the input is the abstract from the BERT paper. And I've printed that out here. And I've asked a couple questions. I asked, what does the B in BERT stand for? And it didn't get it quite right, but it's pretty close. It's understanding kind of the intent of my question mostly. The answer it gave is bidirectional encoder representations from transformers. So it gave me the whole acronym BERT, and I just asked for B, but still pretty cool. And then I also asked BERT, what are some example applications of BERT? What can I use you for? And it correctly highlighted this passage of text, question answering and language inference. So if we go back and look at the abstract, let's see, where is that? Yeah, state-of-the-art models for a wide range of tasks such as question answering and language inference. So again, it understood that BERT large can be used for a number of tasks, such as question answering, and I asked applications. So yeah, pretty impressive. All right, that's it for this notebook. Thank you guys, and I'll see you in the next video.